Welcome to the course Power System Dynamics and Control. So in the last class we were discussing about the uh, different models or different representations of synchronous motion in the stability analysis, and we have seen four types of models, right? That is, one is accurate model, that is the subtransient model. Then we consider the transient two-axis model, then one-axis model, then the classical model. And so classical model is the most simplest model. It is the simplest model, and it is also known as constant flux linkage model, where we're assuming that flux linkage is constant, and also other chains like we can see here, like the input, the governor control action is also here. It is not considered. Okay. So today we'll discuss the small signal stability. So before that, we can just little bit revise what we did in the last class. In the last class, we are stopped at this point when we are discussing the classical or constant flux linkage model, and this is the simplest model, but not very accurate, and this is very useful in case of large power systems, right? And in case of dynamic studies with a time period less than TDO dash are considered, then the field winding dynamics can be neglected, right? In that case, we neglect the field winding dynamics, and also the transient reactance XD dash, which is assumed to be constant, and the transient voltage is computed at steady state and kept constant throughout the study. And also the mechanical torque Tm, which is in fact depends. Please mute yourself. Okay, so Tm also assumed to be constant, which that means your turbine governor dynamics is also eliminated in this case. Hence, the dynamic equations of the model we can write only by these two equations, which are well-known equations. These are the swing equations, right? So first equation gives us the change in this rotor angle, which is nothing but the deviation in the speed, right? Rotor speed. And the second equation is the it is related to the rotor inertia, and it gives us the change in the speed with respect to time. And so this is the well-known equation, so we need not to discuss more on this. This is the classical model, and the equivalent circuit already we derived, and this is the equivalent circuit. So your d-axis and d and q-axis parameters are in fact referred to the common reference frame. When it is referred, it is multiplied with e to the power j delta minus 5 by 2. And similarly the terminal voltage as well, right? And your internal voltage also, it is converted to the common reference frame by multiplying e to the power j delta minus pi by 2. So this is your classical model, and what here we stopped in the last class. So let us see one example how we can initialize the system parameter. So here we can see we have given a three-phase system, where three-phase power system, it is 50 Hz, and the synchronous generator is connected to an infinite bus through a transformer, and there are two parallel transmission lines. As we can see in the figure, we'll see it. The generator is transferring a complex power of 1 plus j 0.25 per unit to the infinite bus. This is the complex power. Then generator parameters are also given. Here are the generator parameters xt, xq, xls, all these parameters are given. And now the question is how to initialize other parameters, which are very much essential to do the dynamic analysis of the power system. So initialize the synchronous generator. The question is this, and this is your system, which is, we can see this is your transmission line with two transmission lines in parallel. And the generator is feeding the power, that is real power 1 per unit, reactive power J of 0.25 is in per unit, right? Okay. And your terminal voltage is represented as Vt theta t. Xt is your transformer reactance, percentage reactance, or you can say in per unit. It is also in per unit. And the reactance of transmission line is also given. V infinity is your voltage of the infinite bus, which is considered here as the reference bus. Therefore, it is taken as 1, 0 degree, right? 1 per unit, 0 degree. The magnitude is 1 per unit and angle is 0 degree. So already we discussed about how to initialize, and when we are discussing, I mentioned that if your system is large, we go for not for single machine infinite bus system. If your system is consisting of more than two machines or two buses, then we need to go for load flow analysis. With the load flow analysis, we can find the initial conditions. That means the terminal voltages and currents at the generator, and then we can initialize different parameters in the system, right? But here it is a only single machine system which is connected to infinite bus. So here infinite bus is considered as another machine, a huge machine, right? In fact, a huge machine can be considered as infinite bus. So here this infinite bus is considered as a huge machine. So therefore it is represented as a huge machine, right? With huge, we can say infinite inertia, right? So therefore we call it infinite bus. And from this, we need to find the terminal conditions, and from there we can initialize different parameters. So in order to find the terminal conditions, I need to find the current, right? So therefore, the terminal current will become, it will be nothing but P minus JQ V conjugate, right? So V infinity conjugate is same. It will remain same because it is a reference bus having magnitude 1 and 0 degree. So the imaginary component is 0 here. So therefore V infinite 0, that is equal to 1 minus J of 0.25. So your terminal current here, the current injected to the infinite bus is 1 minus J 0.25. If we'll convert this into the polar form, then it will get 1.038 angle minus 14.036 degree. So this angle is with reference to the reference bus. That means your current is making an angle of minus 14.036 degree to the reference, that is the V infinite, right? So similarly, we can find the terminal voltage, that is Vt theta t, that is nothing but equal to V infinite plus It into J of the whole combination of the reactances, right? J of xt plus 0.5 into xl. Okay. So that is because these two lines are parallel having equal reactances, therefore it will be divided by 2, so it will become 0.5 xl, and obviously xt is capital T. Xt is your reactance of the transformer. Okay. So now just by adding this, we found the voltage 1.0915 per unit. Angle is 13, that is 13.24 degree. And this angle is nothing but, this is the angle That is, the voltage is making with the infinite bus voltage, right? V infinite. Then similarly, we can find EQ delta. So EQ delta is nothing but your internal voltage. So just by adding the terminal voltage and the impedance, the impedance in the generator, that is Rs plus Jxq into terminal current, that is IT phi t, right? So just by multiplying, we found the internal voltage of the generator, that is coming around 1.5617, and this angle is 37.438. So that means this angle. So in our analysis, it is necessary that this delta should be with reference to the common reference, right? So therefore here also this angle is with reference to the common reference. Here common reference is infinite, right? Okay. So now we can very easily initialize the parameters. We know Vd equal to Vt sine. Just put the equations and initialize. Vd is equal to Vt sine delta minus theta t. Just substituting the values, we can find Vd, then Vq, then Id, IQ, ED dash, EQ dash, EFD, all these just by substituting in the equation, steady state equations of these parameters, we can just find the initial values, right? Similarly, RF, right? RF and VR, all these quantities we can find very easily, right? Similarly, V reference also we can find omega I, omega base, that is under steady state condition, these are all equal, right? Then PSP, that is the valve power, and that is equal to P reference. Then your steam chest power, right? PSP, that is equal. And then your torque developed, mechanical torque developed. Then your electromechanical torque developed. So all these parameters are initialized. Now we can go for the stability analysis. With these initial values, we can go further. So as soon as we find the initial value, we can linearize the system for a small signal stability analysis. Right? We know this from the beginning because we'll do it here. How to do the small signal stability analysis. In case of small signal stability analysis, it is essential to linearize the system because it happens because of the small disturbance, and therefore if we can linearize the system, we can very easily assess the small signal stability. And therefore, in order to linearize the system, we need these initial conditions essentially, because when you linearize, we know how to linearize. We'll also talk about in this class more how to linearize a system. In this class or next class, we'll discuss. Okay. So now, okay. So here, just one more assignment. This is just one assignment I'm giving you. You can note it, or already I have scheduled. You will find this assignment and please submit this. This is related to formation of a reduced Y-bus matrix, right? So here we have a 5-bus system, 5-bus network having nodes 1, 2, 3, 4, 5, right? And it has 2 synchronous generators and one load as shown in figure. We can see here the load is connected at bus 5, right? And the generators are connected at bus 1 and bus 4. This is bus 4. So the per unit reactances of the connecting branches are also mentioned here in the figure. The load is consuming a complex power of 1.8 plus J0.65. This is your complex power consumed by the load. So the voltage also given at the load bus. Okay. Assuming the load to be constant impedance type. So assuming this load as constant impedance type, okay. Already we have done this theoretical analysis we did, right? So now what you have to do, convert the system admittance matrix to reduced admittance matrix with only internal nodes of the generator. So that means you will get a reduced Y-bus matrix, that is, please mute yourself, having the size 2 by 2. Because generally if we'll find the Y-bus matrix for this system, it is general Y-bus matrix is of 5 by 5, right? Now, if we'll find the reduced Y-bus matrix as per our theoretical analysis in the previous class, it should become 2 by 2, right? Considering the internal nodes of the generator, right? So therefore, we need to find this reduced Y-bus matrix. And in the assignment, I have given this problem and I have mentioned that please make a program, MATLAB program, and you should upload your MATLAB program along with your answers with respect to that assignment. I have already scheduled tomorrow. You will get this assignment. Okay. So please submit it. Okay. Okay. So now we'll start the discussion about the small signal stability analysis. So what is this small signal stability analysis? Already you might have studied in your very beginning. I think Professor Siva Subramani has taught you different types of stability, right? Transient stability, small signal stability. That is known as the angular stability as well, right? So small signal stability is the ability of the system to be in synchronism when subjected to small disturbance. That is the small signal stability of a system. So in a power system, we know there is a continual change of load, continual change of generation. It is taking place continuously. It is happening in the system because if you'll see the whole power system, it is an interconnected grid, right? Just imagine Indian power grid. In Indian power grid, we have many generators, right? And also it is very much interconnected. We have 5 regional zones and they are connected in itself in your intra-zonal region, and each zone is connected with high voltage AC lines and DC. Also we can see the loads and the generators are continuously varying. It is difficult to make the system operating under a steady state condition where your generation, that means your sum of generation, becomes equal to the sum of load plus losses in the system. It is difficult to get this balanced condition in a power system under dynamic situation because the power system is always operating in a dynamic condition. Continuously the loads are changing, generation is changing, right? Sometimes the faults happen taking place, sometimes the line is becoming outage, right? There are many events taking place. so therefore different types, therefore the stability analysis is categorized into different types, right? As it is discussed previously. So one of them is small signal stability, right? And it is defined as the ability of the system and by which it remains in synchronism with the system when it is subjected to the small disturbance. What is the meaning of small disturbance? Small disturbance means like the change in load, change in generation, right? Or sometimes the tripping of the lines. They're called the small disturbances. If we'll say large disturbance means if a large chunk of load is disconnected from the system, right? Suppose one of the regional tie line is disconnected suddenly because of some fault. So that means it will hamper the whole system, right? It is a large disturbance. Or sometimes the large fault is taking place. So that way some portion of the system is disconnected from the main system. That also creates a large disturbance. But small disturbance continuously taking place because of the change in the load, change in the generation, right? So, and the system is maintaining the stability irrespective of these small disturbances. How it is maintaining? It is because of the small signal stability of the system. It is the ability of the system. It can make the system, keep the system in synchronism even if there are small disturbances. Sometimes these small disturbances create, it actually, what do you call it? It in fact, it becomes more oscillatory and the system becomes unstable, right? So the disturbances can be switching of small loads, generators, a transmission line tripping. The small signal instability can lead to oscillations in the system. So therefore, sometimes it becomes unstable because of the sustained oscillation in the system. Okay, particularly sometimes it becomes, if we are not taking care of, or we are not putting the proper damping arrangement, right? Damping controller, then sometimes this small signal disturbance also lead to the instability, right? And it is oscillatory in nature. So there are three modes of oscillations due to small disturbances. What are they? First one is your local modes of oscillation. What is this local modes of oscillation? Local modes of oscillation is, it is because of a single generator or group of generators oscillating against the rest of the system. So in a particular power station, if we'll see there are a group of generators. So if those group of generators, if they're oscillating together against the whole other rest of the system, then we call it local modes of oscillation. Then second one is your intra-plant modes of oscillation. It is due to the oscillations among the generators in the same plant. Okay, so inside a plant we have many generators, and if the generators are oscillating among with each other, that is called intra-plant modes of oscillation. So the typical frequencies of oscillations of the local or intra-plant modes are 1 Hz to 2 Hz. So these two modes, one is your local mode and intra-plant mode. The typical range of the frequency is 1 Hz to 2 Hz. Then third one is your inter-area modes of oscillation. This is due to a group of generator in one area oscillating together against another group of generators in a different area. Okay, so therefore this is called inter-area modes of oscillation. That means the group of generator in one area, they're oscillating with the other group of generators in a different area. So the typical frequency range of inter-area mode of oscillations are 0.1 Hz to 0.8 Hz. Okay. So local, intra-plant and inter-area are electromechanical modes of oscillations. These are electromechanical modes of oscillation where we see the rotor angle and the rotor speed, they in fact oscillate with each other, right? We'll see it, and in which the rotor angle and the speed of the generator oscillate. Apart from the electromechanical modes, these three modes are electromechanical modes, right? Local modes, intra-plant mode and inter-area mode, they are called known as electromechanical modes of oscillation. So apart from this electromechanical modes of oscillations, there can be control modes. Okay, so control modes means because of the lack of proper tuning of the controller, like the voltage regulator of an excitation system, and these are called the control mode. Because of that, if some oscillation is taking place, lack of tuning, so that is called the control modes of oscillation. And another mode of oscillation is torsional mode of oscillation. It is due to the oscillations in the turbine generator shafts. Okay, it happens in the turbine generator because turbine is connected with the generator. So because of the oscillation in the shaft of the turbine which is connected to the generator, it is because of the mechanical input. If it is not properly being fed and not be properly being controlled, then this torsional mode of oscillation comes into picture. So the main idea behind small signal stability analysis is that the power system, which is nonlinear, for small disturbances it can be linearized around the steady state operating condition. Therefore, we need the initial conditions, right? Therefore, to analyze the system in order to linearize the system. As the system will be oscillating in a small area around the steady state operating point. Okay. So once the nonlinear system is linearized around an operating point, then linear control theory can be applied. Like we can form the state space model and we can design our controller as per the requirement to assess the stability of the system. So let us do the analysis of fundamental concepts of stability of a dynamic system. So we'll do a generalized discussion and which is also applicable to the power system. If we have a nonlinear system, how we can linearize it and how we can apply this concept of state space model to this, right? So any dynamic system, we can represent this any dynamic system as this, right? That is this is called the state space representation. So x dot t is the state vector and yt is your output vector, right? So your x dot t is the derivative of the state variables is equal to f of xt ut. That means it is a function of xt and ut. Xt is the state variable, ut is your control input variable, right? So yt is the output, which is also a function of gxt ut. So this we can say this is a nonlinear representation, right? So we can linearize it where xt is called a state variable, ut is the control input, yt is the system output. F and g are the functions dependent on the state variable and the control input. For a multi-variable, multi-input, multi-output MIMO linear time invariant system, the equations, this equation particularly can be written as this, right? So for a time invariant linear system, we can write this for a multi-input, multi-output system. We can represent the above equation like this. That is x dot t will be equal to axt plus but, and your yt will be yt, capital Yt, equal to cxt plus dut. Already we know this. This is already we have studied this in linear control system, right? Analysis. So xt is called as the state vector, ut is the control input vector, yt is the output vector, a is the state matrix, b is the input matrix, c is the output matrix, and d is the feed forward matrix. Generally this feed forward path is neglected most of the time because in power system most of the time it is not required feed forward path, right? State variables are the minimum number of variables in a system that can completely define the dynamic behavior of that system. So this is state variable. Okay, so this is your state space representation of the dynamic system, right? Now if we'll write this equation in expanded form, I can write xt as, if we have n number of state variables, it is x1, x2 up to xn. And then the n state variables define the behavior of the system. So state space is the n-dimensional space created by the n state variables. Already we have studied in the linear algebra, elementary linear algebra course, all these things. So applying Laplace transforms to the state space equations and assuming an initial condition XO, we can get these two equations, right? Just by taking Laplace transform of the state space model. So the first equation becomes Sxs minus x naught. This is your initial condition, equal to Axs plus Bus, right? Similarly, your output equation becomes Ys, that is equal to Cxs plus Dus, right? And from this above equation, we can find xss. If we'll just segregate xss, eliminate just by taking this side axs, right? So we'll find that si minus a inverse into x0 plus bus, right? It is easy to find. Now inverse, we can represent this as this adjoint matrix si minus a divided by determinant of si minus a multiplied by xo plus bus, right? Similarly, just by substituting this value here in the output equation in xs, this equation, if we'll substitute here in the output equation ys, we'll find this, right? So your ys will become c of si minus a inverse xo plus bus plus dus, right? Now, suppose the initial condition is taken as 0. If we'll assume that the initial condition is 0 and assume there is no feed forward path, feed forward from the input to the output, right? So then for a single input, single output system, for a CISO system, your equation will look like this, right? So Ys by Us, it is a single input, single output system. For that, if we'll find the transfer function, it will be C of Si minus A inverse into B, right? From this equation, we can reduce if x naught, if we'll assume this as 0, and this feed forward path is not there, means this will be 0, right? This becomes 0. Then Ys will only be having C plus Si minus A inverse Bus, and if we'll take Us to the left hand side, Ys by Us will remain like this, right? Okay, and the inverse is written in this format, that is adjoint Si minus A by determinant of Si minus A. So this equation shows the transfer function between the output Ys and the input Us, right? This is the transfer function of interest. That means with this transfer function we'll do our analysis, stability analysis, right? So denominator in this equation is nth order polynomial, right? If we'll see this, right? Called as the characteristic equation, and the roots of the equations, this characteristic equation, are called the eigenvalues, right? We know this already from the previous courses. We have studied this, right? So then how to find this eigenvalue? Just by equating this with 0. This is a determinant, and if we'll equate to 0, we'll find the characteristic equation which is equated to 0. Now with that condition, we'll find the eigenvalues. If we'll solve this characteristic equation, the roots of the characteristic equation will give us the eigenvalues, right? So now this is a small question. It is already, I have given this as an assignment, another assignment to you. You can do it and send me. So there are few systems given. The transfer function is given, that is Ys by Us, and we need to find, we have to derive the valid state space realizations, and we need to define the state variables, derive the coefficient matrices A, B, C, D, A, B, C, and D, right? So for these three transfer functions, please do this. This is the assignment. Another assignment, I have scheduled this. You will get it tomorrow at 9 a.m. and do this and submit it as PDF file. Okay. So this is another example. If we have a complex transfer function, we can segregate this into two parts, right? And we can do the analysis in the same way we can find the state space model, right? Okay. So now we'll do some analysis on eigen properties. This is in fact very much essential in the stability analysis. What is this eigen properties? So the eigenvalues corresponding to the state matrix A have certain properties. We call it eigen properties, right? So let the n eigenvalues be represented as lambda 1, lambda 2 up to lambda n. Then for an ith eigenvalue, I can write for ith eigenvalue I can write a into phi I equal to lambda I. Lambda I is your ith eigenvalue into phi I, right? So this phi I in fact known as the right eigenvector, right? Already we have studied this in your in the elementary linear algebra course. This kind of equation we have seen already, right? A into phi I. A is your system matrix, right? Or state matrix. A into phi I into equal to lambda I into phi I. That means your right eigenvector corresponding to the ith eigenvalue, if multiplied together, it is nothing but it is equal to A matrix, that is state matrix multiplied with the right eigenvector of the ith corresponding to the ith eigenvalue. So if we'll manipulate this equation, we'll get again A minus lambda I into phi I equal to 0, right? Just little bit manipulation if we'll do from this equation, we'll find this, right? And now this is your right eigenvector corresponding to eigenvalue lambda I. And similarly, we have another vector, we call it left eigenvector, which is multiplied before the A matrix, that is psi matrix, psi I A equal to lambda I psi I, right? So here this even we can adjust manipulating, we'll find psi I equal to A minus lambda I. I is your identity matrix equal to 0. And psi A is your left eigenvector corresponding to the eigenvalue lambda I. Okay. So now we have two vectors corresponding to the ith eigenvalue, right? So corresponding to ith eigenvalue, we have two vectors. One is called left eigenvector, other one is right eigenvector. So similarly to each of the eigenvalues, we'll have two vectors, right? So one is your right eigenvector, other one is your left eigenvector. So if I'll expand, I'll write this right eigenvector in the expanded form, this I can write it as the element of the right eigenvector will be phi 1I. It is a column vector, phi 2I dotted f to phi ni, right? Similarly, your left eigenvalue, left eigenvector is a row vector. This left eigenvector corresponding to the ith eigenvalue will be having the elements psi I1, psi I2 dotted up to psi In. Okay, this is your left eigenvector. So it will exist for all the eigenvalues, and we know in the linear algebra course we have studied that this right eigenvector and left eigenvector, they're orthogonal. That means your psi j into psi I is equal to 0 when j is not equal to I. If it becomes equal, that means for the same eigenvalue, if we'll multiply the left and right eigenvector, then it will give us a constant value. We can see here for ith eigenvalue, if we'll multiply the left eigenvector psi I into phi I, that will give me a constant, that is Ci. Okay, so just multiply, this is a row vector multiplied with a column vector, it will give me a constant value, right? And if we'll multiply the eigenvector of others, right? It's like different eigenvector, left eigenvector and right eigenvector of different eigenvalues for different eigenvalues, then it becomes always 0. Therefore, they are orthogonal to each other, right? Psi j into phi I equal to 0 when j is not equal to I. So where Ci is a constant, usually this equation can be normalized so that the maximum value will be 1, right? So it is normalized under this condition. When it will normalizing means if we'll divide this by Ci both the side, then it will become 1, right? So that means psi I phi I by Ci will be equal to 1. So if we in the normalized form, we can just represent like for unit form we represent like that. If we just dividing Ci both, we will get Ci and phi I. This is a normalized form of representation. Just same we can take. So it will become equal to 1, right? This is under normalized condition. Okay. Now, so this is under normalized condition, your psi I into phi I is equal to 1. Okay. So now if we'll see, let the right and left eigenvector matrices be defined as this. So for if we'll consider the right eigenvector for all eigenvalues and put it together, it will become a matrix and we'll call it right eigenvector matrix. Similarly, if we'll put together the left eigenvectors for all eigenvalues, it will also form a matrix. We'll call it left eigenvector matrix. So let us represent this left and right eigenvector matrices in this form. So you know this phi is a column vector, right? Phi 1, phi 2, phi n, they're column vectors, they're combined together to form a matrix of n by n, right? Similarly here also there are row vectors psi 1, psi 2, psi n. We are taking the transpose, that means it is becoming a column vector, right? So a column vector combined together, it is a matrix, and again we are taking a transpose, so it becomes again n by n matrix, right? Okay. So we know this is valid because they are orthogonal. Psi j is phi I equal to 0 and psi I and phi I equal to Ci. And in the normalized condition, phi I psi I into phi I equal to 1. So in the matrix form, if we multiply your phi and psi together, that means psi into phi will give me an identity matrix. If I multiply, you can see it. It will give me an identity matrix. And therefore, I can write psi matrix, that is left eigenvector matrix, is equal to the inverse of the right eigenvector matrix. So this is valid under normalized condition. That means when the eigenvectors are normalized, under that condition, your psi is equal to phi inverse. So now let us consider a n-dimensional diagonal matrix of eigenvalues that is defined as this. So we are assuming a diagonal matrix. Let us represent one diagonal matrix consisting of all the eigenvalues as the diagonal element, and other off diagonal elements are 0, right? So now if I'll just this is a representation and we'll replace it here in this equation. How it is we can see here. So we know this equation, your system state matrix, if it is multiplied with the right eigenvector corresponding to ith eigenvalue, that will be equal to the ith eigenvalue multiplied with the same right eigenvector, right? So then in the matrix form, if I'll write this, right, if I'll write this in the matrix form, I can write it A into phi, that is equal to phi of this diagonal matrix, right? Just in the matrix form, if I'll write for all the eigenvalues, right? Considering all the eigenvalues, if I'll write this in the matrix form, this equation, right? So then if I'll multiply the right eigenvector matrix with A, then obviously your right eigenvector matrix will be multiplied with the diagonal matrix, right? So that diagonal matrix consisting of eigenvalues as the diagonal elements, right? Okay. So because we know this will, if we'll expand this, it will give me phi 1 lambda 1, right? Like this, it will give me phi 1 lambda 1, phi 2 lambda 2, phi 3 lambda 3, like this, phi n lambda n. So this is nothing but this is also an n by n matrix, right? Okay. So this is also an n by n matrix. So this is equal to phi of phi of the diagonal matrix consisting of all the eigenvalues as the diagonal elements. Okay. So now with this equation, in this equation, if we'll pre-multiply, that is phi inverse, how it will look like. If we'll pre-multiply phi inverse here, then obviously your diagonal matrix will become equal to phi inverse A phi, right? So phi inverse is nothing but psi and a normalized condition. So therefore I can write it is equal to psi A phi, right? So this will give me your diagonal matrix in which all the diagonal elements are the eigenvalues of the system matrix or the state matrix. So these three matrices in fact plays very important role in the stability analysis. One is your psi, that is the left eigenvector matrix, and another one is your phi, that is right eigenvector matrix. Another is your diagonal matrix whose diagonal elements are all eigenvalues. They're all of size n by n. Psi is also size of n by n, phi is also size of n by n, and the diagonal matrix is also of size n by n. And all these three matrices are called modal matrices. So through these three matrices, we'll do the modal analysis of the stability of the system, right? So we can see it in the later slides, right? So let us do this modal analysis for a homogeneous system. So if we'll consider a homogeneous or unforced system, so in order to understand the stability of the system, let us consider first a homogeneous or unforced system. That means there is no external input to the system and the response is natural. Okay. So then in that condition, the dynamic system, if we'll see your equation, if we'll take the control input vector as 0, your state space representation will become x dot will be equal to axt. Okay, so there will be ut will be 0 here, right? Because it is a homogeneous or unforced system, right? So the stability of a system can be better understood through the use of modal matrices rather than the state matrix A. So how it is, we'll see, right? This is because the state matrix is not a diagonal matrix, hence cross coupling terms between states will be present, right? So we write, if we'll represent the state matrix, so there will be always cross coupling terms. So already we can see from this equation, right? So we can see it will write it as a11 x1 plus a12 x2 dotted up to a1n xn, right? Similarly a21 x1, a22 x2, right? a2n xn, all this up to n, right? Up to n dimension we can write. So you can see these terms. These terms are all, if we'll find, they're all sum of the product of coefficient terms and the state elements, right? Or different states. So that means one state is represented in all other states, right? That therefore we call it cross coupling terms. These terms are cross coupling terms. That means one state. So the derivative of one state is not represented as only the same state. It is in fact the sum of the products of the all other states, right? Okay. So therefore the cross coupling terms are present when we represent in the state space form. If we'll consider the modal matrix in under that condition, there will be no cross coupling terms. So let us define a new state vector, that is xt equal to phi of zt. Phi, we know phi is your right eigenvector matrix into zt, right? So xt is n by 1, n cross 1, and phi is n by 1, n, and zt is n by 1. So finally, the dimension is matching, right? So let us define this state vector in terms of phi zt. This is another, if we'll represent it in this form. So we can write just by substituting xt in the above equation, in this equation, what we'll get? Phi of z dot t equal to a phi zt, right? Okay. So just by substituting xt equal to phi zt here in this equation, right? So we'll find this equation now. So considering this, now just multiplying phi inverse both the side, we'll get z dot t equal to phi inverse a phi zt. So we know phi inverse is psi, so psi a phi. This will give me the diagonal matrix having all the eigenvalues as the diagonal elements. So therefore, I can write this as diagonal matrix into zt, right? Now it is a diagonal element having, so therefore now I can, if we'll write z dot 1, right? So it will give me, it is a, sorry, if I'll write it just expanded form, if I'll write z1 dot z2 dot up to zn dot equal to lambda 1 0 0 dotted up to lambda 2, then here 0 0, every all elements will be 0, then finally it is lambda n into zt z1 z2 dotted up to zn. If we'll write the equation for first state variable, that is z1 dot, I can write it as lambda 1 z1, right? So now it is in the decoupled form, right? There is no cross coupling. So z2 dot will become lambda 2 z2. Similarly, your zn dot will become lambda n zn, right? So that means I'm representing the derivative of the state, particular state, as a function of that particular state variable, right, with a constant multiplied. That constant is nothing but the eigenvalues. That means if we know the eigenvalue, we can directly get the solution from this equation. Directly I can write z1t is equal to something, right, like zo or some initial condition, right, z1o and e to the power lambda 1t, like this. That directly I can write because there is no cross coupling terms. So this is the advantage we get when we use this modal matrix, or we call it diagonal matrix. We convert this state equation, which is written in the cross coupling form, we can write that in the decoupled form, right? This is called decoupled representation, right? So now we can see it. So therefore, since the matrix, diagonal matrix is a diagonal, this matrix is a diagonal matrix with eigenvalues as its elements. So therefore, each dynamic state can be represented in terms of single variable leading to the decoupling of the states, right? Now your states are decoupled. Okay. So now I can write zi dot t is equal to lambda I zi t. So it is valid for all I equal to 1 to n. So the solution of the above equation we can find very easily with the initial condition as zi naught. I can find very easily that will give me zit will become equal to e to the power lambda it zio. Zio is your initial condition. It is valid for all the states, right? N states. So from this equation, the stability of the system can be assessed very easily, right? Very easily. If all the eigenvalues are on the left half of the S-plane, that is the real part of the eigenvalues should be having a negative value, then the system is stable. So already we have already studied this. You in your uh, control courses might be. So from the above equation, it can be seen that with the eigenvalues on the left side of S-plane, as time moves towards infinite, the state variables will reach their initial conditions, making the system stable. So this is called asymptotic stability. Okay. So if at least one of the eigenvalues is on the right side of the S-plane, that is real part of the eigenvalue is positive, then the system is unstable. With at least one eigenvalue with positive real part, it can be observed from the equation, this equation, right? It can be observed that the state variable can never come back to its initial condition. This is called as aperiodic instability. So from this equation, if from the nature of the eigenvalues, we can easily find the stability of the system. So this is called aperiodic instability. So the eigenvalues of a system with a real state matrix have complex conjugate pairs of eigenvalues. If at least one of the complex conjugate pair lies on the imaginary axis of the S-plane, then the system becomes oscillatory. This is called oscillatory instability. Okay. So when one of the eigenvalues is lying on the imaginary axis, right? If at least one eigenvalue is on the origin, then the system stability cannot be assessed. Okay. So therefore, we know xt is equal to phi of zt. And from this equation, the initial value of the original state vector in terms of the new state vector can be written. I can write this as x naught will be equal to phi of z naught, right? So from this I can find z naught is equal to phi inverse x naught. Phi inverse is psi, so psi x naught. So if I'll write one element that is ith state vector, initial condition zio will be equal to psi I xo. So we know this equation zit is equal to e to the power lambda it zio. It is valid for all state variables, all the states, right? So now xt is equal to phi of zt. So if we'll expand it in the vector form, phi 1, phi 2, phi, and they're all column vectors. They're multiplied with all the states. We'll find the combination of this phi 1 z1t, phi 2 z2t, and it is nothing but sum of phi I zit I equal to I is varying from 1 to n, right? Summation of I equal to 1 to n phi I zit. Okay. So what we can see here, since the new state variables zt are directly related to the eigenvalues and each of the new state variables corresponds to exactly one eigenvalue. So it can be observed from the equation that the right eigenvector phi I corresponds to the activity of the state variables, right? So this right eigenvector, in fact, phi I, it corresponds to the activity of the state variables xt in the ith mode, right? So we have seen that xt is nothing but we consider this xt is equal to phi of zt, right? So if we'll expand this, we have seen that xit will be nothing but, we'll see this, xit xt is nothing but, sorry, let me, so xt we have seen xt is this one, xt is this, right? So if we'll find one of the element, if I'll write xjt, suppose I will write xjt, so it will be your sum of I equal to 1 to n, sorry, is phi of ji zit, like this it will be. And we can see here, so this indicates that uh, this phi I, this corresponds to the activity of the state variable xj, right? So this phi ji, it in fact corresponds to the activity of xj in this particular mode, right? Okay, ith mode. So that is what it indicates. So I think the time is going beyond 5. So we'll stop here. We'll uh, do this analysis in the next class, maybe tomorrow at 10 o'clock. There are more analysis based on this. So we'll come to that, because one is your phi I will correspond to the activity of the state variable, then psi I will represent the contribution of the state variable to the particular mode, right? So all these things we'll discuss in the next class. So we'll stop here. Okay, so thank you very much.